Distributive Laws of Vector Algebra. Welcome, everyone. Today, we are going to explore a fundamental aspect of vector algebra, the distributive laws. Now, as you delve deeper into studying vectors, you'll find that when we multiply a vector by a scalar, which is just a regular number, there aren't just random results. Instead, there are specific algebraic rules that govern how these scalar multiplications interact with vector addition and even with other scalar multiplications. We refer to these specific rules as the distributive laws. It is important to understand that these laws aren't just arbitrary formulas to memorize. They are essential because they ensure that our algebraic manipulations, the math we do on paper, remain perfectly consistent with the geometric reality and the physical directions that vectors represent in the real world. Over the next few slides, we will break down each of these laws one by one with clear examples. 1. Distributivity of scalar addition over vector multiplication. Now that we've introduced the concept of the distributive laws, let's dive into our first specific rule, the distributivity of scalar addition over vector multiplication. Take a look at the formula on the screen. K a vector plus m, a vector equals the quantity k plus m, all multiplied by the vector a. In plain English, this law tells us that if we take a single vector and multiply it by two different numbers, or scalars, and then add those two resulting vectors together, we get the exact same result as if we had simply added the two scalars together first and then multiplied that total sum by our original vector. To make sure this is clear, let's break it down step by step. First, we start with our base vector, a. Next, we scale this vector by a factor of k, which gives us ka. Then, we take that same original vector and scale it by a different factor, m, giving us ma because these two vectors are pointing in the same or opposite directions, meaning they are collinear. When we add them together, the total length is simply the sum of the two scales. This results in a final vector that is exactly k plus m times our original vector, a. We'll see a great practical example of this in the next slide involving wind speeds. Real-world example for distributivity of scalar addition. Now, to help you visualize the first law we just discussed, the distributivity of scalar addition, let's look at a practical scenario. Imagine we have a constant wind blowing towards the east, and we can represent this initial wind strength using the vector a. Suppose that first, the wind strength increases, and it is now moving at 2 times its original speed, which we write as 2a. Later on, the wind picks up even more, increasing by another 3 times its original speed, represented by the vector 3a. To find the total wind strength acting on us, we simply need to find the sum of these two vectors, which is 2a plus 3a. Now, applying the law of distributivity that we saw on the previous slide, we can simplify this calculation. Instead of adding the vectors separately, we can add the scalars first. This means the total strength is the same as the wind blowing at 5 times its original speed, which is written as 2 plus 3, all multiplied by vector a, resulting in 5a. As you can see, the math stays consistent whether we scale the vectors individually or combine the multipliers first. 2. Associativity of scalar multiplication. Now that we have seen how to combine scalars when they are acting on the same vector, let's move on to our second law, the associativity of scalar multiplication. The law is written as k parentheses m vector a equals parentheses km vector a. What this law is telling us is that when a vector is being scaled multiple times, the order in which you apply those scalars doesn't actually change your final result. In practical terms, this means you have a choice in how you perform the calculation. You can either scale the vector sequentially, meaning you apply the first scalar, then apply the second one to that new result, or you can simply multiply the two scalars together first and then apply that single product to the vector. It's a much more flexible way to handle multiple scaling factors. In the next slide, I'll walk you through a step-by-step breakdown of how this works mathematically. Step-by-step explanation for associativity of scalar multiplication. First, let's start with a simple foundation. We take a single vector, which we'll call vector A. Next, we apply our first scaling factor. We multiply vector A by a scalar, let's call it m, which gives us a new scaled vector, m vector A. Now, to demonstrate the associative property, we take this newly created vector and multiply it by another scalar. K. This gives us the expression k, all multiplied by the quantity m vector A. As you can see, the final result is mathematically identical to a much simpler process. You could simply multiply the two scalars, k and m, together first to get the product km, and then multiply your original vector A by that single combined scalar. It shows that when you're scaling a vector multiple times, the order in which you group those scalars doesn't change your final destination. We'll see a practical application of this concept with a map scaling example in the next slide. Now that we have seen the mathematical law for associativity, let's break it down step by step so you can see exactly how it works in practice. Real-world example for associativity of scalar multiplication. Now, to help you visualize the associative law we just discussed in the previous slide, let's look at a practical example involving a map. Imagine you are looking at a map where a displacement of 1 centimeter represents our base vector, A. Suppose you decide to zoom in on a specific area by a factor of 3. In vector terms, we are scaling our original vector by a scalar m, which is 3, so our vector becomes 3a. But what if you decide to zoom in even further by another factor of 2? This means we are now scaling our already enlarged vector by a scalar k, which is 2. Mathematically, we write this as 2 multiplied by the quantity 3a. As you can see, this is exactly the same as if you had performed a single, larger zoom by a total factor of 6, because 2 times 3 equals 6. This results in the final vector being 6a. This perfectly demonstrates the associative law. Whether you scale the vector in 2 separate steps or multiply the scalars together first, the final magnitude and direction remain identical. 3. Distributivity of a scalar over vectors. Take a look at the formula here. K multiplied by the quantity a vector plus b vector equals k times a vector plus k times b vector. In plain English, what this law is telling us is that if you have 2 different vectors and you find their resultant, which is just their sum, scaling that total sum by a factor of k gives you the exact same result as if you had scaled each individual vector by k first and then added them together. It shows us that the scaling factor applies uniformly across the entire addition. Now that we have explored how scalars interact with a single vector through addition and associativity, let's move on to our third and final law, the distributivity of a scalar over vectors. Step-by-step explanation for distributivity of a scalar over vectors. First, let's start with 2 distinct vectors, which we will call vector A and vector B. The first way to approach this is to find their sum, or what we call the resultant vector, which is vector A plus vector B. Once we have this single resultant vector, we can multiply it by a scalar. Let's call it k. This gives us the expression k times the quantity vector A plus vector B. Alternatively, we can take a different path to reach the same destination. Instead of adding the vectors first, we can multiply each individual vector by the scalar k separately. This gives us k times vector A and k times vector B. If we then add these 2 scaled vectors together, we get k times vector A plus k times vector. As you can see, whether we scale the sum or scale the individual parts before adding, both methods yield the exact same final vector. This is the essence of the distributive law we are studying. Now that we have seen the law itself on the previous slide, let's break down exactly how this process works step by step. In the next slide, I'll show you a practical example involving physical forces to help you visualize this in action. Real-world example for distributivity of a scalar over vectors. Imagine you have an object, and 2 different forces are pulling on it at the same time. We can represent the first force as vector F1 and the second force as vector F2. To find the total force acting on the object, we simply add them together, so total force equals F1 plus F2. Now, suppose we decide to double the intensity of both of these forces. In our algebraic terms, our scalar, K, is equal to 2. If we apply this to our total force, we are looking at 2 multiplied by the quantity, F1 plus F2. But here is the beauty of the distributive law. You can achieve that same result by doubling each force individually before adding them. So, if you double the first force to get 2F1 and double the second force to get 2F2, and then find their sum, you end up with 2F1 plus 2F2. As you can see, both methods lead you to the exact same resultant force. This perfectly demonstrates that scaling the sum is identical to scaling each part of the sum separately. Now, let's bring this third law, the distributivity of a scalar over vectors, into a practical context so you can see it in action. Common mistakes to avoid. Now, before we wrap up and look at our final summary, I want to pause and discuss some common pitfalls. Even if you understand the laws we've just covered, it is very easy to make certain errors in your calculations. First, let's talk about confusing scalars with vectors. When you are writing your solutions, please be very careful to place the vector arrow over your letters. It is crucial to remember the distinction we've made throughout this lesson. Letters like K and M represent simple numbers or scalars, whereas A and B represent vectors. A very common mistake is writing K plus a vector. This is mathematically incorrect because, as we've seen, you cannot add a scalar to a vector. They are different types of mathematical objects. Second, watch out for incorrect distribution. In our previous slides, we looked at how a scalar can be distributed over a sum of vectors. However, some students mistakenly try to distribute a vector over another vector, writing something like a vector multiplied by the quantity b vector plus c vector. Please remember, in the context of the distributive laws we are studying today, distribution only occurs when a scalar is multiplied by a vector or a sum of vectors. Finally, keep an eye out for sign errors. This is particularly important when dealing with negative numbers. When your scalar k is negative, remember that it doesn't just change the magnitude, it actually reverses the direction of the vector. For example, if you have -1 multiplied by the quantity a vector plus b vector, the result is negative a vector minus b vector. Keep these 3 points in mind to ensure your algebraic manipulations remain accurate as we move into our final key takeaways. Key takeaways. First, we looked at the distributivity of scalar addition over vector multiplication. Remember, when you have the same vector being multiplied by two different numbers, you can simply combine those numbers. In mathematical terms, k a vector plus m, a vector equals the quantity k plus m, all multiplied by a vector. Just remember, if the vector is the same, you can combine the scalars. Second, we discussed the associativity of scalar multiplication. This tells us that when you are scaling a vector multiple times, the order of the scalars doesn't matter. Whether you write k applied to m a vector, or you multiply the scalars first to get k times m, all multiplied by a vector, the result is identical. It is as simple as multiplying the scalars together first. Finally, we covered the distributivity of a scalar over vectors. This is where you apply a single scale factor to a sum of different vectors. As we saw with our force example, k multiplied by the quantity, a vector plus b vector, is exactly the same as k a vector plus kb vector. You are simply distributing that scalar to each individual vector in the sum. All right, we have reached the end of our lesson. Before we wrap up, let's quickly recap the 3 fundamental laws we've covered today to ensure you have a solid grasp of these distributive properties. Keep these 3 rules in mind, and always be careful not to confuse your scalars with your vectors, as we discussed in our common mistakes slide. Great job today!